For as long as humans have stood beneath the night sky, we have looked up and felt something ancient and quiet settle in our bones, a sense of order. The stars did not flicker in panic. The moon did not vanish without warning. The sun rose, as it always had, painting the world in gold, then withdrew with dignified grace. This rhythm was not just beautiful, it was trustworthy. It gave us calendars, navigation, mythology, and eventually science. We came to believe the cosmos was a grand clockwork, wound tight by some unseen hand, ticking with perfect, eternal precision. But what if that trust was misplaced? What if the sky so serene, so dependable, was hiding a secret so unsettling that it would unravel our deepest assumptions about predictability, control, and even destiny? Imagine standing on a hilltop 3,000 years ago. You are a Babylonian astronomer, your eyes sharp from decades of watching. You've mapped the paths of planets, recorded eclipses, predicted solstices. You believe you understand the heavens. Then, one night, you notice something strange: 3 bright stars, close together, not fixed in their places like the others, but shifting, sometimes drawing near, sometimes flinging apart. Their dance erratic, impossible to chart with your clay tablets, and cuneiform. You try to find a pattern. You fail. Again and again you fail. That moment, the first human confrontation with the three-body problem, was not just a scientific puzzle, it was a quiet betrayal. Because the universe, it turns out, is not always a clock. Sometimes it is a storm, and the storm begins with just 3, not 100, not 1,000,000. Just 3 celestial bodies, 3 suns or 2 stars and a planet, or a moon caught between 2 giants, bound by gravity, tugging at one another in an endless, invisible tug of war. With 2 bodies, everything is calm. The Earth orbits the Sun in a graceful ellipse. The Moon circles the Earth with reassuring regularity. Newton showed us why. 2 masses under gravity follow paths we can write down with a single equation. Predictable, elegant, safe. But add a third, just one more, and the math cracks open like thin ice underfoot. Suddenly, there are no neat formulas, no eternal cycles, no guarantees. The paths twist, loop, slingshot, collide, or fling one body into the void, all depending on the tiniest, almost imperceptible difference in starting position or speed. Change the angle of one orbit by less than the width of a human hair seen from a kilometer away, and over time, the entire system unravels into something utterly different. This is not randomness. It is something far more disturbing: deterministic chaos. The future is fully determined by the laws of physics, yet it is unknowable in practice. Not because we lack intelligence, but because the universe itself refuses to be pinned down. And this truth, that even the simplest addition of a third body can turn cosmic harmony into pandemonium, has haunted science for over 3 centuries. It haunted Isaac Newton, who, despite conquering the heavens with his laws of motion and universal gravitation, confessed in private letters that the motions of the moon, tugged not just by Earth, but also by the distant sun, gave him headaches no equation could soothe. He called it so very difficult a problem. It haunted Henri Poincare, the brilliant French mathematician who, in the 1890s, entered a competition to prove the stability of the solar system. He thought he had solved it, until he discovered a fatal flaw in his own work. In correcting it, he accidentally gave birth to chaos theory, revealing that some systems are so sensitive to initial conditions that long-term prediction is impossible, not due to ignorance, but by nature's design. And it haunts us today, not just as an abstract puzzle, but as a real, observable phenomenon in the stars above. We now know of actual triple-star systems scattered across our galaxy. Some are stable for eons. Others are cosmic powder kegs, where planets, if they exist, are flung into darkness or roasted by erratic stellar flares. In one such system, GW Orionis, astronomers have seen a planet-forming disk torn into misaligned rings, as if the stars themselves are fighting over the raw material of worlds. This is not science fiction. This is the universe as it truly is, breathtakingly beautiful, deeply mathematical, and fundamentally unpredictable in its most intimate configurations. The three-body problem is more than a challenge for physicists. It is a mirror held up to human ambition. We want to know. We want to control. We build telescopes, launch probes, simulate galaxies on supercomputers, all in the hope that if we look closely enough, the cosmos will reveal its blueprint. But the three-body problem whispers back. Not everything can be known. And yet here is the wonder: within that chaos, islands of order still emerge. There are moments, configurations, rhythms where three bodies move in perfect, silent harmony. These are rare, fleeting, but they exist. And we have learned to find them, to use them, even to sail our spacecraft through them like cosmic currents. So this story is not one of despair. It is a story of humility and awe. Because to understand the three-body problem is to stand at the edge of human knowledge and feel the wind of the unknown on your face. It is to realize that the universe does not owe us predictability, but it does offer mystery. And in that mystery, there is beauty deeper than any clockwork. In the next chapter, we return to the moment it all began, to a man in a quiet English countryside watching an apple fall and dreaming of a universe he thought he could fully understand. We return to Newton and to the problem he could not solve. In the winter of 1665, a young man named Isaac Newton sat alone in his family home in Woolsthorpe, England, the countryside blanketed in snow, the plague keeping the world at bay. Cambridge University had closed its doors, and the 23-year-old scholar, quiet, intense, prone to fits of obsessive focus, found himself with nothing but time, books, and the vast silence of the English winter. It was here, legend says, beneath an apple tree, that he watched a fruit fall and asked a question no one had dared to connect before. If the apple falls because of Earth's pull, does the moon fall too? That question simple, almost childlike, ignited a revolution. Newton realized that the same force pulling the apple to the ground must also be tugging at the moon, bending its path into a curve around the Earth. Gravity, he proposed, was not a local quirk of our planet, but a universal law, an invisible thread connecting every particle of matter across the cosmos. With this insight, he forged a new language, calculus, a mathematics of change, and with it, he wrote down equations that could describe not just falling apples, but the orbits of planets, the tides of oceans, the trajectories of comets. In 1687, he published Philosophia Naturalis Principia Mathematica, the Principia, and the universe, for the first time in human history, seemed legible. Two bodies under gravity, solved, completely, elegantly. Given their masses, positions, and velocities, Newton's laws could predict their motion for all time. The Earth and Sun, a stable ellipse. Jupiter and its moons, perfectly calculable. Even Halley's comet, that ghostly wanderer, returned right on schedule in 1758, exactly as Newton's mathematics had foretold. It was a triumph so profound that it reshaped civilization. Clockmakers began modeling orreries, miniature solar systems spinning in perfect harmony. Philosophers declared that if the heavens obeyed laws, perhaps so did human society. The Enlightenment bloomed on the certainty that the universe was rational, orderly, and knowable. But even as the world celebrated, Newton himself knew there was a crack in the foundation, because the real solar system does not contain just 2 bodies. It contains 8 planets, dozens of moons, asteroids, comets, and the sun. Every one of them tugs on every other. The moon is pulled by Earth, yes, but also by the sun. Jupiter's immense gravity tugs on Mars, on Saturn, even on the distant comets in the Oort cloud. These are not minor corrections. They are constant, subtle disturbances, what astronomers call perturbations. And when Newton tried to calculate the moon's motion with full precision, accounting for the sun's influence, he found himself lost in a thicket of equations with no clear path out. He wrote to his friend Richard Bentley, "The perturbation of the moon's motion by the sun is so intricate that I have not been able to reduce it to a perfect theory." He wasn't alone. For decades after Newton, the greatest mathematical minds of Europe, Euler, Lagrange, Laplace, threw themselves at the problem. They developed new techniques, approximations, series expansions. They got closer, but never exact, never complete. The issue wasn't lack of effort, it was structural. With 2 bodies, the system has what mathematicians call integrals of motion. Quantities that remain constant, like energy, angular momentum, and the orientation of the orbital plane. These conserved quantities act like guardrails, confining the motion to a predictable path. But add a 3rd body, and those guardrails vanish. The system gains degrees of freedom it cannot contain. The equations become non-integrable, meaning there is no general formula, no closed-form solution that works for all possible starting conditions. This wasn't just a technical inconvenience, it was a philosophical earthquake. Because if even the moon, our closest celestial companion, could not be perfectly predicted using the very laws that explained everything else, then perhaps the clockwork universe was an illusion. Perhaps the cosmos was not a machine, but something far more alive, responsive, and unruly. Yet for over a century, scientists hoped the problem was merely difficult, not impossible. They assumed that with better math, better observations, better patience, the 3-body problem would eventually yield. After all, the solar system seemed stable. Planets didn't crash. Moons didn't vanish. The sky still kept time, mostly. So they pressed on. In the late 1700s, Pierre-Simon Laplace declared confidently that if an intellect, what we now call Laplace's demon, knew the position and momentum of every particle in the universe, it could compute the entire future and past with perfect accuracy. Determinism reigned. Chaos was just ignorance. But Laplace had never truly solved the 3-body problem. He had only shown that, for certain configurations, the solar system appeared stable over long time scales, thanks to resonances, averaging effects, and sheer luck. He had papered over the cracks with approximations, not filled them with truth. The real reckoning would come a century later, not from an astronomer, but from a mathematician who entered a contest he never expected to lose. In 1885, King Oscar II of Sweden, an avid patron of science, announced a prize to mark his 60th birthday, a gold medal and 2,500 kronor to whoever could prove that the solar system was stable over infinite time using Newtonian mechanics. It was the ultimate test of the clockwork dream. Henri Poincare, then a rising star in French mathematics, submitted a memoir. He believed he had succeeded. His work was dense, brilliant, and seemed to confirm that planetary orbits, while perturbed, would never spiral into chaos. The judges, among them the great mathematician Carl Weierstrass, were impressed. They awarded him the prize. But as Poincare prepared his paper for publication, he discovered a mistake, a tiny oversight in how he handled certain trajectories. When he corrected it, something terrifying emerged. Instead of smooth, predictable paths, his equations revealed a tangle of infinitely complex curves, so sensitive that two orbits starting almost identically would diverge wildly over time. He realized that in the three-body problem there were no repeating cycles, no stable patterns guaranteed for all time. The system could appear orderly for centuries, then without warning eject one body into space or send two crashing together. Poincare had not proven stability. He had discovered instability. He wrote, with quiet devastation, "One is struck by the complexity of this figure, which I shall not even attempt to draw." Nothing can give a better idea of the complexity of the three-body problem. The prize was still awarded, but the dream of a perfectly predictable cosmos was shattered. Poincare's work was so ahead of its time that few understood its implications. It would take another 70 years until the age of computers for chaos theory to be born anew. But in that moment, in the late 1880s, the three-body problem ceased to be a mere technical hurdle. It became a symbol, a reminder that even in a universe governed by precise laws, certainty has limits. Newton had given us the laws, but he left us a riddle he could not solve, a symphony he began but never finished. And in the silence between its notes, the universe whispers its most unsettling truth, that order and chaos are not opposites, but partners in an endless cosmic dance. In the next chapter, we step into that dance. We meet the strange, beautiful, and terrifying world of deterministic chaos, where the future is written in stone, yet impossible to read. Imagine you're standing on the edge of a vast, dark lake at midnight. The surface is still, reflecting the stars like polished obsidian. You drop a single pebble into the water. Ripples spread outward, orderly, concentric, predictable. Now imagine dropping a second pebble nearby. The ripples intersect, interfere, create new patterns. But still, with enough math, you could trace every crest and trough. Now drop a third. Suddenly, the surface churns. Waves collide, amplify, cancel, rebound off unseen shores. What was once calm becomes a seething mosaic of motion. And if you tried to predict the exact shape of the water 1 minute from now, down to the last droplet, you'd fail. Not because the laws of physics are broken, but because the system is too sensitive, too entangled, too alive with feedback. This is the essence of chaos. And in the cosmos, gravity is the pebble. The three-body problem is the universe's most elegant demonstration of deterministic chaos. A phenomenon where the future is entirely governed by fixed laws, yet remains fundamentally unpredictable in practice. It is not randomness. It is not magic. It is the consequence of nonlinearity, when small causes produce effects that grow exponentially over time, twisting certainty into doubt. To understand this, we must abandon the idea that deterministic means predictable. Newton's laws are deterministic. Given exact initial conditions, they dictate exactly what happens next. But here's the catch. We can never know those initial conditions with infinite precision. Not in measurement, not in theory, not even in principle. And in a chaotic system, that tiny uncertainty, smaller than the width of an atom, smaller than the flicker of a photon, doesn't stay small. It snowballs. This is the butterfly effect, though the name came much later. The poet Edward Lorenz in the 1960s discovered it while running weather simulations on an early computer. He reran a model, typing in a number rounded from 0.506127 to 0.506, and watched as the entire forecast diverged into a completely different storm pattern. He later asked, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" The answer in chaotic systems is yes. Not because butterflies control weather, but because the atmosphere, like the three-body problem, is exquisitely sensitive to initial conditions. But Poincare saw this a century earlier. While studying the motion of three gravitating bodies, he realized that their trajectories could be represented as paths on a geometric surface, an abstract landscape of all possible states. In a stable two-body system, those paths are smooth loops like grooves on a record. But in the three-body case, Poincare found something astonishing. The paths didn't loop. They twisted, folded, crossed over themselves infinitely, creating a structure so intricate it defied drawing. He called it homoclinic tangle, a web of trajectories so interwoven that any two starting points, no matter how close, would eventually be torn apart by the system's internal dynamics. This was the birth of chaos theory, though it would lie dormant for decades, buried in dense mathematical journals. What makes the three-body problem chaotic isn't the number of bodies, it's the way gravity couples them. Gravity is a long-range, non-linear force. The pull between any two bodies depends on the inverse square of their distance. But when a third body enters the scene, it doesn't just add a new force. It changes the distances between the first two, which changes their mutual pull, which changes their motion, which changes how they affect the third, and so on, in an endless feedback loop. There is no shortcut, no averaging trick that works forever, no hidden symmetry that saves the day, except in very special cases, which we'll visit later. To see this in action, consider a simple thought experiment. Place two stars in a tight orbit around each other, a binary pair. Now introduce a third star far away, moving slowly. At first, nothing dramatic happens. The binary dances undisturbed. The third star drifts like a distant spectator. But over time, the third star's gravity tugs ever so slightly on the binary, altering its orbit by a hair's breadth. That tiny change alters how the binary tugs back on the third star. After hundreds or thousands of orbits, those minuscule nudges accumulate. Then suddenly, the third star swings close. In a violent gravitational slingshot, it steals energy from the binary, flinging one of the stars outward at tremendous speed. The remaining two settle into a tighter orbit. The ejected star becomes a rogue, wandering the galaxy alone. This isn't rare. Astronomers call it the three-body interaction, and it's one of the main ways stars get kicked out of clusters. It's also how some black holes merge through chaotic encounters in dense stellar neighborhoods. But here's what's haunting. If you replayed this scenario with the third star's position shifted by less than the diameter of a proton, the outcome might be completely different. Maybe no ejection occurs. Maybe a collision happens instead. Maybe all three settle into a temporary dance before unraveling centuries later. The laws are the same. The difference is imperceptible at the start, but cosmic in the end. This is why the three-body problem has no general solution. Not because we're not smart enough, but because the universe itself encodes infinite complexity in finite configurations. Every triple system is its own unique story, with no template to follow. And yet, amid this chaos, there is structure. Poincare's tangle isn't random. It has fractal geometry, self-similar patterns repeating at ever smaller scales. Zoom in on a region of possible motions, and you'll find the same complexity as in the whole. This fractal nature means that even in chaos, there is mathematical beauty, a hidden order beneath the turbulence. Modern simulations reveal this vividly. When scientists plot the outcomes of thousands of three-body experiments, varying masses, speeds, angles, they don't get a smooth distribution. They get a mosaic of stability and instability, interwoven like stained glass. Some initial conditions lead to quick ejections. Others produce long-lived, quasi-stable orbits. And a vanishingly small set lead to perfect repeating choreographies where all three bodies trace the same path in turn, like dancers in a cosmic ballet. But these are islands in an ocean of uncertainty. For most configurations, the future is a fog. We can simulate it step by step using computers to calculate each tiny gravitational tug. But even the best simulation is only as good as its starting data. And since we can never measure position or velocity with infinite precision, every forecast has an expiration date. In the solar system, that date is surprisingly long. Hundreds of millions of years, thanks to the vast distances between planets and the sun's overwhelming dominance. But in a tight triple-star system, chaos can erupt in decades. This isn't just theoretical. In 2019, astronomers observed a star in our galaxy, named HD 106906, being flung away at high speed, likely the result of a three-body encounter in its youth. Its trajectory points back to a binary system, now quiet, as if nothing happened. But the scar remains in the runaway star's path. So the three-body problem teaches us a profound lesson. The universe is not hostile to prediction. It simply sets boundaries on it. Within those boundaries, science thrives. Beyond them, we must learn to live with uncertainty. And that's okay. Because chaos is not the enemy of understanding. It is a deeper layer of it. In the next chapter, we search for the oases within this storm, those rare, miraculous configurations where three bodies move, not in chaos, but in harmony. Places where the universe, against all odds, finds a rhythm.